Hello viewers, in today's session we'll start learning time response analysis. Now if you talk about response is nothing but reflex of any particular system with respect to a given input. You call that as a response. If it is found out in terms of time domain, then you call it as time response. And coming to analysis, it's nothing but learning the behavior of a particular system with respect to the given input and the obtained response, that you call it as analysis. Now, as we know, this is the representation of a closed loop system where you have a forward path and a return path here. Now, the time response of the particular system is the output of the closed loop system as a function of time. Then you call it as a time response. That is represented by C of t in t domain. Closed loop transfer function is nothing but C of s equal to R of s into G of s by 1 plus G of s into H of s. Usually transfer function is C of s by R of s. You are talking about the response, so it is in terms of C of s here. Now this is in terms of s domain. Now for the response in t domain, that is in time domain, C of t is nothing but Laplace inverse of C of s equal to Laplace inverse of G of s by 1 plus G of s into H of s. This is about the general representation of time response of a closed loop system. Now, time response is usually of two parts here. One is transient response plus steady state response. A transient response is nothing but the response of the system when the input changes from one state to another. For example, if this is the graphical representation and you have an input, now this particular part where the system is changing from one state to another here with respect to time, then this is nothing but the transient response. And the steady state response is nothing but the response when t approaches infinity. So this part you call it as a steady state response. This is a usual representation. For learning about the response of a system, we are supposed to have the knowledge of the input signal. That is because we need to predict the response of a system. For this reason, we are supposed to know about the information regarding the input signal so that we can assess the output signal or the response of the system. For this reason, depending upon the various characteristics of the input signals, we do have certain standard test signals to test that particular system so that we come to know about the behavior in terms of time response of that particular system. Now, standard test signals. Now, these are the standard test signals: step signal, ramp signal, parabolic signal, impulse, and sinusoidal. Now, the very first signal is step signal here. Now, this step signal is nothing but a signal whose value changes from 0 to a at t equal to 0 and remains constant for t greater than 0. Can you observe it here? Now, this step signal is representing an actual steady input to a system. Now, if it is a unit step signal, then A is nothing but unity here. This is the general representation of step signal, that A will be equal to unity here, where u of t equal to 1 for t greater than equal to 0 and it is equal to 0 t less than 0 here. Okay, this is about step signal. Now, the second one is the ramp signal. The ramp signal is a signal whose value increases linearly with time from initial value of 0, that is at t equal to 0. Now, if you observe here, it's linearly increasing. Now, with respect to time t increasing here, you can observe the value here increasing. Okay. Now, the ramp signal resemblance with a constant velocity input to the system. Now here, if it is an unit ramp signal, then A would be equal to unity, that is nothing but 1 here. Now this is the generalized mathematical representation here, R of t equal to A into t for t greater than or equal to 0 here. Now equal to 0 for t less than 0. Now the next signal is parabolic signal. In parabolic signal, the instantaneous value varies as square of the time from initial value of 0 here. Usual graphical representative graph you would get in terms of a parabola, and this parabolic signal resembles a constant acceleration input to the system. And if it is a unit parabolic signal, then A is nothing but unity, or A equal to 1 here. This is the mathematical representation where R of t equal to A into t square by 2 for t greater than or equal to 0, and it is equal to 0 for t less than 0. The next signal we have impulse signal. A signal which is available for a very short duration is called impulse signal here. Now in this graphical representation, ideal impulse signal is an unit impulse signal which is defined as a signal having 0 values at all times except at t equal to 0. Mathematical representation is delta of t equal to 0 for t not equal to 0 here. This is a shortcut representing the whole signals, that is step here in terms of t domain and in terms of s domain here. The very first one is step R of t is A in terms of s domain in Laplace form, that is A by s. If it is unit step, it is 1, that is in terms of s domain it is 1 by s. If it is ramp, A into t, in terms of s domain A by s square. If it is unit ramp, that is A equal to 1, so it is t, and in terms of s domain 1 by s square. If it is parabolic, the mathematical representation is A t square by 2, that is in terms of s domain A by s cube. Now if it is unit parabolic, A equal to 1, so it is t square by 2, so in terms of s domain 1 by s cube. In terms of impulse, delta of t, that is the representation, that is in terms of R of s, that is 1 here. This representation is only to remember these signals easily in terms of t domain expression and also in terms of s domain, so that we need this information while solving the problems, so that solving would be easy. If you find this video useful, please do like, share and subscribe.